Group 16 elements ncert part. Oxygen, sulfur, selenium, tellurium and polonium constitute group 16 of the periodic table. This is sometimes known as group of chalcogens. The name is derived from the Greek word for brass and points to the association of sulfur and its congeners with copper. Most copper minerals contain either oxygen or sulfur and frequently the other members of the group. Occurrence: oxygen is the most abundant of all the elements on Earth. Oxygen forms about 46.6% by mass of Earth crust. Dry air contains 20.946% oxygen by volume. You can take approximately 21. Fine. However, the abundance of sulfur in the earth crust is only 0.03 to 0.1%, very less. Combined sulfur exists primarily as sulfates such as gypsum. Gypsum is CaSO4 2H2O, Epsom salt MgSO4 7H2O, barytes BaSO4, and sulfides such as galena, galena is PbS, zinc blend ZnS, copper pyrites CuFeS2. Traces of sulfur occur as hydrogen sulfide in volcanoes. Organic materials such as eggs, proteins, garlic, onion, mustard, hair, and wool contain sulfur. So all these you need to remember because anything can convert into question. Selenium and tellurium are also found as metals, selenides and tellurides in sulfide ores. Polonium occurs in nature as a decay product of thorium and uranium minerals. The important atomic and physical properties of group 16 along with the electronic configuration are given in table 7.6. We'll see the table also. Some of the atomic and atomic physical and chemical properties and the trends are discussed below. Electronic configuration. The elements of group 16 have 6 electrons in the outermost shell, have ns2 np4 general electronic configuration. Atomic and ionic radii. Due to increase in the number of shells, atomic and ionic radii increases from top to bottom in the group. The size of oxygen atom is, however, exceptionally small. Ionization enthalpy. Ionization enthalpy decreases down the group. It is due to increase in size. However, the elements of this group have lower ionization enthalpy values compared to those of group 15 in the periodic table. This is due to the fact that group 15 elements have extra stable half-filled p orbitals. So this half-filled electronic configuration is the reason. Because of the compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. Interesting point is sulfur, selenium, tellurium, polonium and oxygen is the least. However, from sulfur onwards, the value again becomes less negative up to polonium. Oxygen is least than polonium. Remember this point. Next to fluorine, oxygen has the highest electronegativity value among the elements. Within the group, electronegativity decreases with an increase in atomic number. This implies that the metallic character increases from oxygen to polonium. Here is a question. Elements of group 16 generally show lower value of first ionization enthalpy compared to the corresponding periods of group 15. Why? Again, half-filled stability is the reason. Physical properties. Some of the physical properties of group 16 elements are given in table 7.6. Oxygen and sulfur are non-metals. Selenium and tellurium metalloids, whereas polonium is a metal. Polonium is radioactive and a short-lived half-life 13.8 days. All these elements exhibit allotropy. The melting and boiling points increase with an increase in atomic number down the group. The large difference between the melting and boiling points of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as diatomic molecule O2, whereas sulfur exists as polyatomic molecule like S8. Oxidation states, trends in chemical reactivity. The elements of group 16 exhibit a number of oxidation states. The stability of -2 oxidation state decreases down the group. Polonium hardly shows -2 oxidation state. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2, except in the case of OF2, where its oxidation state is +2. Other elements of the group exhibit +2, +4, +6 oxidation states, but +4 and +6 are more common. Sulfur, selenium, tellurium usually show +4 oxidation state in their compounds with oxygen and +6 with fluorine. So with oxygen plus 4, with fluorine plus 6. Remember this point. The stability of plus 6 oxidation state decreases down the group, and stability of plus 4 oxidation state increases. Inert pair effect. Bonding in plus 4 and plus 6 oxidation states is primarily covalent. Higher oxidation states are generally covalent. So here is a table. In the table, let me check atomic numbers 8, 16, 34, 52, 84. Atomic masses increasing, electronic configuration same, covalent radius gradually increasing, nothing special. Ionic radius increasing, nothing special. Electron gain enthalpy, as I told you, oxygen minus 141, which is less than polonium minus 174. Ionization enthalpy decreasing, nothing special. Electronegativity 3.50 for oxygen, 2.58, 2.55. Sulfur, selenium very close, decreasing down the group. Density increasing, but polonium it is not mentioned. Melting points increasing, but polonium is less than tellurium. Boiling points increasing, but polonium is less than tellurium. Oxidation states, we know oxygen shows minus 2, minus 1, plus 1, plus 2. Sulfur minus 2, plus 2, plus 4, plus 6. Selenium also same, tellurium also same, and polonium plus 2, plus 4. So coming to anomalous behavior of oxygen. Right. The anomalous behavior of oxygen, like other members of P block present in second period, is due to its small size and high electronegativity. One typical example of efforts of small size and high electronegativity is the presence of strong hydrogen bonding in water, which is not found in H2S. The absence of d orbitals in oxygen limits its covalency to 4 and in practice rarely exceeds 2. H3O plus you can expect where 3, but 4 we didn't notice 4. Okay, these lines are not there. On the other hand, in case of other elements of the group, the valence shells can be expanded and covalence exceeds 4, 6. Okay, now you can go up to 6, SF6. Reactivity with hydrogen. All the elements of group 16 form hydrates of the type H2E. Oxygen, sulfur, selenium, tellurium, polonium is given by E. Some properties of hydrates are given in table 7.7. Their acidic character increases from water to tellurium, H2TE. First point. The increase in acidic character can be explained in terms of decrease in bond enthalpy for the dissociation of He bond down the group. So bond enthalpy decreases, acidic character increases. Owing to the decrease in enthalpy for the dissociation of He bond down the group, so bond energy decreasing, the thermal stability hydrates also decreases from H2O to H2PO. As bond energy decreasing, thermal stability also decreases. All the hydrates except water possesses reducing property, and this character increases. Reducing property is increasing and water is not a reducing agent. So this property is stable. Melting points, water is highest because of hydrogen bonding. Then from H2S to H2T increasing. Boiling points, water is highest. Then increasing from H2S to H2T. Bond distance, water to H2T increasing. Bond angle, water 104, 104.5 na? It is given 104 here. H2S 92, H2SE 91, H2T 90. Delta H formation, water is minus 286, H2S is minus 20, H2S is plus 73 and H2T is 100. That means decreasing. So obviously H in kilojoules is given, dissociation constants are given. Water 10 to the power of minus 16, then gradually it is increasing 10 to the power minus 7, minus 4, minus 3. So acidic strength around the group increases. Reactivity with oxygen. All these elements form oxides of the EO2 and EO3 types where E is the same. Ozone and sulfur dioxide are gases while selenium dioxide is solid. You can expect these lines in NEET and JEE. Selenium dioxide is solid. Reducing property of dioxides decreases from SO2 to SeO2. SO2 is a reducing agent while TeO2 is an oxidizing agent. Remember, this is a question. SO2 reducing agent while TeO2 is oxidizing agent. Why? Do you know the reason? Can you expect the reason? SO2, sulfur plus 4, it tends to plus 6. So it is undergoing oxidation, so reducing agent. Simple line. Besides EO2 type, sulfur, selenium, tellurium also form EO3 type of oxides like SO3, SeO3, TeO3. Both type of oxides are acidic in nature. Important line. Reactivity towards the halogens, elements of the group 16 form a large number of halides of the type EX6, EX4, EX2 and E2X2, where E is the element of this group and so. X is the halogen, right? The stability of the halide decreases in the order of fluoride, chloride, bromide, iodide. Fluoride is more. Fluoride greater than, chloride greater than, bromide greater than iodide. Amongst the hexahalides, hexafluorides are the only stable halides. All hexafluorides are gaseous in nature. They have octahedral structure. Sulfur hexafluoride SF6 is exceptionally stable for steric reasons. So this line you remember. Amongst tetrafluorides, SF4 is a gas, SeF4 is liquid, TeF4 is solid. Question: SF4 gas, SeF4 liquid, TeF4 is solid. And remember these points when you mention when you are teaching, okay, now then definitely students will like, because students always try to remember the exceptional points. And teacher, if you are as a teacher, if you are focusing on those, that is going to be a good job. These fluorides have sp3d hybridization and thus have trigonal bipyramidal structures in which one of the equatorial positions is occupied by a lone pair of electrons. This geometry is also regarded as seesaw. We know, okay, sp3d, one lone pair, seesaw. All elements except oxygen form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral structure. The well-known monohalides are dimeric in nature. Examples are S2F2, S2Cl2, S2Br2, Se2Cl2, Se2Br2. These dimeric halides undergo disproportionation as given below. 2Se2Cl2 gives rise to SeCl4 and selenium. Here is a question. H2S is less acidic than H2TE. Why? Simple, bond energy. Due to decrease in bond dissociation enthalpy down the group, acidic character increases. List the important sources of sulfur. Write the order of thermal stability of the hydrates of group 16 elements. Why is H2O is liquid and H2S is gas? Hydrogen bonding. Coming to dioxygen. Okay, now we'll complete dioxygen also in this session. We'll go with ozone in next one. Dioxygen. Preparation. Dioxygen can be obtained in the laboratory by the following ways: by heating oxygen containing salts such as chlorates, KClO3, on heating use KCl and O2. Nitrates, NaNO3, on heating use NaNO2 and O2. And permanganates, KMNO4, on heating use K2MNO4, MNO2 and O2. Okay, but only one equation is mentioned here. By the thermal decomposition of the oxides of metals low in the electrochemical series and higher oxides of some metals. Ag2O, heating use Ag and O2. HGO, Hg and O2. Pb3O4, PbO and O2. PbO2, PbO and O2. Hydrogen peroxide is readily decomposed into water and dioxygen by catalysts such as finely divided metals and manganese dioxide. Remember this point, this is very important. H2O2 can be broken into water and oxygen by manganese dioxide catalyst. On large scale, it can be prepared from water or air. Electrolysis of water leads to the release of hydrogen at the cathode and oxygen at the anode. Industrially, dioxin is obtained from air by first removing carbon dioxide and water vapor, and then the remaining gases are liquefied and fractionally distilled to give dinitrogen and dioxygen. This point we were discussing even nitrogen also. Coming to the properties. Dioxygen is a colorless and odorless gas. Not a very important point. Its solubility in water is to the extent of 3.08 centimeter cube in 100 cc water at 293 Kelvin, which is just sufficient for the vital support of marine and aquatic life. Okay, for fishes and all, right? It liquefies at 90 Kelvin and freezes at 55 Kelvin. Oxygen atom has 3 stable isotopes, 16, 17 and 18. Molecular oxygen is unique in being paramagnetic in spite of having even number of electrons. Class 11, chemical bonding, we remember this for a long time. Dioxygen directly reacts with nearly all metals and non-metals except some metals like gold and platinum and some noble gases. Its combination with other elements is often strongly exothermic, which helps in sustaining the reaction. However, to initiate the reaction, some external heating is required as bond dissociation enthalpy of oxygen double bond is high, 493.4 kilojoules per mole. I think you remember nitrogen triple bond also. Yes, 941.4. Good. Some of the reactions of dioxygen with metals and non-metals and other compounds are given below. Calcium, calcium oxide, aluminium, Al2O3, P4, P4O10, C, CO2, ZnS, ZnO and SO2, CH4, CO2 and water. Some compounds are catalytically oxidized. For example, 2SO2 plus O2 gives rise to 2SO3. The catalyst is V2O5. 4HCl plus O2 CuCl2 is the catalyst which changes to Cl2 and water. In addition to its importance in normal respiration and combustion processes, oxygen is used in oxyacetylene welding, in the manufacture of many metals, particularly steel. Oxygen cylinders are widely used in hospitals, high altitude flying, and in mountaineering also. The combustion of fuels, hydrazines in liquid oxygen provides tremendous thrust in rockets. Then some simple oxides are mentioned here. A binary compound of oxygen with another element is called oxide. As already stated, oxygen reacts with the most of the elements of the periodic table to form oxides. In many cases, one element forms two or more oxides. The oxides vary widely in their nature and properties. Here, so many chances of questions are there for your JEE mains as well as a NEET examination. See, advanced also you can expect. Oxides can be simple like MgO, Al2O3 or mixed Pb3O4, Fe3O4. Simple oxides can be classified on the basis of their acidic, basic and amphoteric character. An oxide that combines with water to give an acid is termed as acidic oxide. SO2, Cl2O7, CO2, N2O5. For example, SO2 gives H2SO3. As a general rule, only non-metal oxides are acidic, but oxides of some metals in high oxidation state also have acidic character. This is your question. Mn2O7, CrO3, V2O5 are acidic. The oxides which give a base with water are known as basic oxides like Na2O, CaO, BaO. CaO gives CaOH taken twice. Example given here. In general, metallic oxides are basic. Some metallic oxides exhibit dual behavior like Al2O3, zinc oxide and all. They show characteristics of both acidic as well as basic oxides. Such oxides are known as amphoteric oxides. They react with acids as well as alkalis. For example, Al2O3. Al2O3 with HCl gives AlH2O taken twice. That's close to blah 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 reactions. Okay, now simple remember. Aluminum reacts with HCl, releases H2. Aluminum reacts with NaOH, releases H2. This is important question. There are some oxides which are neither acidic nor basic. Such oxides are known as neutral oxides. Examples are NO, N2O and CO. Thank you.